So in the nucleus, we have the 2 protons and 2 neutrons. This would be for a helium nucleus here. And we know that the 2 protons do not want to be together. We have the electrostatic repulsion between those two. We know, force equals K Q1 Q2 over R squared, Coulomb's law. And those particles want to be apart from each other. So huge question here is, why does the nucleus not want to blow apart? And so there must be something stronger than the electrostatic repulsion, those two particles trying to get away from each other. So it turns out it's the strong force, and the strong force is sometimes called the strong nuclear force, that is responsible to hold the nucleus together, which is represented by these arrows pointing inward between the particles. And so the strong force is many times greater or many times stronger than the electrostatic force. And it's again another fundamental force here that is holding the nucleus together. So as we talk about the fundamental forces, we've talked about the force of gravitation, and we think about the force of gravitation. It's a very small force, right? It's a very weak force. We used this simulation way back, and in this simulation we can see that even if we have a decent amount of mass here, the amount of force is very, very tiny. I just crossed that one out, but the 0.00000000754 newtons, very small amount of force of attraction. And so, but it works over long distances. If we think of planetary motion, the force of gravitation acts over a very long distance. And so that's one of the fundamental forces, the force of gravitation. But then in the nucleus, we have the strong nuclear force, and that is, again, stronger than the electrostatic force, and that's 2 and 3, the fundamental forces. And the strong nuclear force is stronger than the electrostatic force. However, it only works on a very, very small range, very small distance. Those particles, as soon as those particles start to separate here, if the nucleus just separates just a little bit, the electrostatic repulsion will cause the nucleus to go apart quickly. But yeah, as long as it's a very, very small distance, it's the strongest out of the fundamental forces and holds the nucleus together. So by shooting electrons and protons at the nuclei, scientists were able to determine the size, approximate size of the nucleus, and they determined that the density of the nucleus is the same for all nuclei, no matter how big the nucleus is. We've got the same kind of density. And nucleons can only interact with a few nucleons at a time because of the short range of the force. So if you have, let's say, a uranium nucleus, let's say you had 235 nucleons, I would have to do 235 circles here. This nucleon right here, whether it's a proton or a neutron, is not even interacting with this one in terms of the strong force. It's only interacting with the ones that are close to it. And whereas, with the electrostatic force, that can work over a longer range. And so, but again, the strong nuclear force is holding that nucleus together, overcoming the electrostatic repulsion. So what if there are too many neutrons or protons in the nucleus? We have a nucleus here with protons and neutrons is representing, nucleus here. What ends up happening is that the weak nuclear force, which is the 4th fundamental force that we're talking about, changes protons into neutrons. It also can change neutrons into protons. If there are too many of one kind, it can change, the weak nuclear force can change from one to the other. And as we get into elementary particles, which will be the next unit, we'll talk about the weak nuclear force in more detail and how that exactly happens.